Megan Podlaski, and this is our work on electrothermal modeling of fuel cells and batteries for the CHEETA aircraft. CHEETA is a NASA ULI that explores future technologies in electrified aircraft. Our aircraft is designed to be powered using liquid hydrogen fuel cells and batteries with the components in the system cryogenically cooled using liquid hydrogen to reduce losses and system weight. We're studying a system that's at an early stage of development, so we rely on multi-domain models to understand how the subsystems interact with one another. We have limited opportunities for testing and building physical prototypes, so simulation studies assist in sizing analysis, trade-off studies, and give us insight on which designs will have the most benefit to the aircraft. Our aircraft consists of multiple novel components where we have to consider different domains in our models, such as the electrical domain, the thermal domain, mechanical domain, and aerodynamics, as well as the control schema for each of these subsystems. Today, we're going to be looking at our electrical and thermal models for the battery and the fuel cell. Here on the right, we have our electrical system architecture for the CHEETA system. It's a hybrid, centralized, and distributed electrical architecture. There's 3 areas for propulsion, 2 on the wings, 1 on the body. We connect the batteries to each of these propulsion bus bars to better distribute the weight and increase the reliability of the system. We also have 3 bus bars for the fuel cells that are connected to one another via tie line to balance power between generation. First, we look at our fuel cell subsystem. We utilize a proton exchange membrane or PEM fuel cell for our fuel cell model. The purpose of picking the PEM technology is because it requires a less complex power electronic subsystem to integrate the fuel cell with the rest of the electrical system, resulting in a lower fuel cell subsystem weight. The losses in our fuel cell are dependent on both the electrical and the thermal behavior. We consider 3 losses: ohmic due to the electron transport, activation losses due to electrochemical reactions within the fuel cell, and concentration losses due to mass transfer. We get a circuit as shown on the right, which consists of a voltage source representing the voltage produced by the fuel cell, 3 resistive losses for those 3 losses in our fuel cell that are dependent on electrical and thermal characteristics such as the current produced by the fuel cell, pressures within the fuel cell, and temperatures within the fuel cell. So we re-implement the model in the Nahir Dynamic Modeling and Simulation of PEM Fuel Cells reference text using the Medelic programming language, which is an object-oriented modeling language. We re-implement this in the Dymola development environment as shown on the right. All of the equations from that reference text are located within this fuel cell model, which has inputs to define the pressure of the anode and the cathode of the fuel cell, as well as inputs to integrate the model with the electrical and thermal domains of our aircraft. So first we have our electrical connection, which communicates the voltage and current produced by the fuel cell to the rest of the electrical system defined as V out. And then we have our thermal connections T room and T out, which are our thermal connections that communicate temperature and heat transfer with the rest of the cooling system. This model was published in Simulink, so we validate our behavior to make sure that our model was re-implemented correctly. We parameterize both models using the experiment data from the Avista Labs 500 watt PEM fuel cell stack. We export the model that we developed in Dymola using the functional mockup interface imported into Simulink to ensure that we're simulating both models in the same environment using the same initial conditions, integration methods, and solvers. We provide the same current input to both fuel cell models, and we get the same voltage response. This means we've re-implemented our model correctly, and we can now study it with a single branch of the CHEETA electrical system. So next we take that fuel cell model and we integrate it with one branch of our CHEETA system. We scale down the power requirements of the drivetrain because we do not have parameters for a larger, higher powered fuel cell defined yet. So everything is operating at the 500 watt level. We simulate the system for cruise behavior because this would be the scenario in which the fuel cell would be providing the entirety of the power to the drivetrain during flight and the batteries would be powered off. For this cruise behavior, we get our fuel cell voltage and fuel cell current as shown on the bottom. We have a pretty steady response in both the voltage and the current provided to the drivetrain. Next, we look at our battery model. We create an electro-thermal battery model using the Dassault battery library. The electrical and thermal characteristics correspond to values in a lookup table, and those values were determined by experiments conducted on a lithium-ion battery. Our battery model, shown in Dymola, is shown on the right. It consists of a lumped cell model where all the cells are scaled in parallel to give us energy capacity and in series to provide voltage energy potential to the circuit. So the electrical scaling is shown in block A and the thermal scaling is shown in block B. We have our thermal domain represented with the housing heat port component to link us to the cold plate and provide a temperature and heat flow to the cold plate like we saw in the fuel cell model, and then P and N are positive and negative electrical pins of our fuel cell, of our battery, providing voltage and current to be communicated with the rest of the circuit. We want to study this battery model for different cold plate designs to understand how the operating temperature affects our battery's dynamics and how the battery's internal resistances change according to temperature. This is important to understand for fault and other trade studies. So we set a circuit up where our battery is connected in series to a resistive load where we're going to apply a step change to that load. And then we apply a constant boundary condition simulating an environment where the cold plate would be operating at 0C, 20C, and 40C. So we apply a step change to the resistive load that's connected to the battery. It steps down from 10 ohms to 1 ohm. And we plot the resistance per cell, the internal ohmic resistance within the cells down at the bottom of the screen. We have a higher ohmic resistance at a lower cold plate temperature, which is consistent with other studies done on lithium-ion batteries. We also see a more severe spike in the internal resistance when we apply this step change to the load, which would affect the dynamics, especially during a case of a fault. When we look at the battery's current draw and the voltage, we also have a lower operating power for the battery at lower temperatures as the chemical reaction within the battery is slower. These tests give us insight on how we can optimize the cold plate design to reduce losses and achieve maximum power transfer. So in conclusion, our CHEETA project was tasked with developing a design for a fully electrical commercial aircraft. We're using hydrogen-based fuel and a liquid cryogenic cooling in this aircraft, so it was necessary to understand design trade-offs using multi-domain models. Here, today in this work, we created physics-based models of a battery and fuel cells and applied them to electrical and thermal studies. For the fuel cell, we showed we could develop an electro-thermal model, validate that model against previous models, and study how it operates in steady states with the electric drivetrain for the aircraft. And then with the battery, we developed an electro-thermal model to understand how the cold plate operating temperature affects our battery's losses and dynamic response. So in the future, we could apply it to different fault studies and trade-off studies, and it could assist in the design of our battery management system. Thank you for your attention, and I will take any questions. Thanks.